Okay, so today we're going to be doing something pretty cool, which is talking about the fact that Besicovitch sets are generic. So let's remember what a Besicovitch set is. So Besicovitch set is in R2. It is a compact set of measure 0, such that it contains a unit line segment, in every direction. Okay, so we will actually be dealing with not like a full. The ones that we'll be talking about will actually contain line segments only in a range of angles. So like an angle, like some range of angles from -π/4 to π/4 or something like that. But of course, if you have something like this, if you have a Besicovitch set, if you have some range of angles, then you just take a few of those guys. You take 4 of those guys and you put them together, and then you end up with an actual Besicovitch set. So there is here's one way of constructing Besicovitch sets. It's like this. You start off with a triangle like this. Okay, you say, okay, well, I've got a pretty good range of I've got a range of angles, from here over to here, but the area of my set is big. Okay, so what I want to do is I'm going to chop this in half, and then I'm going to slide over one of the pieces. Okay, I'm going to slide over one of the pieces. I end up with something like this. Slide over one of the pieces, and I end up with something like this. Okay, and so you're still going to have that full range, same range of angles, right? But the area of your set is going to be small. Right? Okay, and so that's the first move. Second move is to, instead of chopping in 2, chop it in 4. Okay, you chop it in 4, and you do this in pairs. Okay, you do this in pairs, and you end up with 2. So this guy you slide over. You slide over this guy, and you end up with something like this with some overlap. Maybe more overlap than that. With some overlap. You have this guy, and you slide this thing over. Right? You slide this guy, you slide it over, and you end up with something like this with some overlap. Right? And you keep on. You do this in 4, in 8, in 16, blah blah blah. You keep on going, and the area of the set at each point becomes smaller, and you end up in the limit you end up with something. At least in this way, you can create a set that has all line segments in all directions and is arbitrarily small. Okay. And there's a way of constructing them so that they have measure 0. And what we're going to see today is that in fact that's not unusual. In fact, Besicovitch sets are generic. So, so let's recall what we did. What we talked about last time. You create a distance, right? So recall you have A and B that are subsets of R2, right? And you have some delta, right? And we say that the distance, the Hausdorff distance between A and B is the infimum of the delta. Infimum of the delta such that B is contained in the delta neighborhood of A, and A is contained in the delta neighborhood of B, right? So remember, you take, basically you take every point in the set and you cover it with a delta ball, right? You take the union of all those delta balls, and that's going to be the delta neighborhood, right? So you're saying that, yeah, the distance between two sets is the smallest fattening such that A is contained in the delta fattening of B and B is contained in the delta fattening of A. Okay. So we created this distance. It turns out that, I'm just going to put this as a fact, that the set of compact sets in R2 with the above distance form a complete metric space. And in fact, the next set we define will be closed in this topology, and thus also a compact metric space. I'm sorry, also a complete metric space. So this is sort of bad. Let me define the set. The set that I say is going to also be a compact metric space. So a complete metric space. Okay. So let's let K. Let's take an R. Sorry. Let K. Lowercase cursive K. Denote the collection of all sets, denote the collection of all sets K in R2 such that 1, K is contained in Q, which is the unit Q, -1, half, cross 0, 1. So it's contained in half, cross 0, 0, 1. So this is Q. Okay. And it's closed. Closed in the R2 tuple, in R2, of course. Yeah. 2, K is a union of line segments. We call this line L0 and this line L1 from L0 to L1. So the previous thing that we were looking at, would work, right? It's a collections of line segments, right? Connecting the bottom to the top, right? And for every angle theta between -π/4 and π/4, there exists an L in K, a line segment in K. So I should say contained in K. There's a line segment in K, making that angle with the y-axis. Okay, so you're going to have you're going to have angles between -π/4 and π/4. every angle, there's a line segment with that angle. Okay. Okay. And okay. So so these guys are, this is the space in which our Besicovitch sets are going to be points. So the theorem that we want to prove is that the set of the collection of sets here of measure 0 is generic. And is a generic subset of K, of cursive K. Okay. In other words, Besicovitch sets are the collection of Besicovitch sets is a generic set. So we're going to want to realize this thing as a generic set, right? That's to say, it's going to be a complement of a set of first category, right? It's going to be a complement of a set of first category. Okay. Here's how we're going to do it. We are going to create, the key will be to consider particular subsets of, so here's the key, here are the key subsets. They're called cursive K, Y naught epsilon, and they are subsets of cursive K. So here's how we're going to find them. Okay. So for each y naught in 0, 1, and each epsilon greater than 0, let K be in cursive K. So let K be one of these sets that's a union of line segments. Okay. And we're going to say, so we say K is in this class, K Y naught epsilon, if something happens. Okay. So K Y naught epsilon is going to be the union of these guys that have certain properties, and here they are. Here it is. If we say that K is in this class, if there exists an eta such that the one-dimensional Lebesgue measure of the set of x in negative a half and half, such that xy is in the fattening of K, is the eta fattening of K is smaller than 10 epsilon. If this happens for all y in y naught minus epsilon, y naught plus epsilon. So cursive K y naught epsilon is the, I'll let you copy that. Okay, so what does it say? It says that if there exists a fattening of k, right? So k is a union of line segments, right? Such that for every angle you have a line segment. Okay, you have a line segment making that angle with y-axis. If there's a fattening of that guy, such that for all, so y naught is some height here. So let's say y naught is here. Y naught is some height. Epsilon is some small number, right? So here's y naught plus epsilon, y naught. This height is y naught. This height is y naught plus epsilon. This height is y naught minus epsilon. Okay. And what we're saying is that for every y in this range, for every line of a height within this range, right, the intersection, the one-dimensional Lebesgue measure of the intersection of that line. So you take a line, you run it through, and you look at the intersection of that line with the fattened set. Okay. If there exists an eta such that for every line, the intersection of that line with the fattened set is smaller, the measure of that is smaller than 10 epsilon. Is smaller than 10 epsilon. Then we say that this k is in the k y naught epsilon class. Okay. Does that make sense? And you look at the you have your set. You know, it's some collection of line segments, right? You fatten up the set. And you look at the intersection. So if there exists a fattening so that every intersection of lines with the fattening has a one-dimensional measure of smaller than 10 epsilon, then we say that we're in that set. Okay. So these guys turn out to be the key class. This is what we're going to use. So here's the important fact about them. That for each y naught in 0, 1, and each epsilon greater than 0, cursive y naught epsilon is open and dense. Open and dense in cursive. Notice that, recall or be reminded or be informed that being open and dense means that the set being open and dense is equivalent to its complement being closed, of course, and nowhere dense. So being open and dense implies that you're generic. Okay. So open and dense implies generic. Because your complement is a set first category. Okay. So let's So let's prove the theorem. So remember, is the theorem that a set of guys of measure 0 is generic. Okay, so let's assume the lemma and prove the theorem right now, and then we'll go back and prove the lemma, which is awful. Well, it's not awful, but it's very, it's sort of like, you know, there's some mathematics where you're sort of standing at a distance and then you're like applying tools, right? And then there's some mathematics where you get in and you just get your hands very dirty. Right? You don't use tools, but it's a very like bare hand, dirty hand sort of thing. The proof will be very dirty. Like the difference between hard analysis, soft analysis, and hard analysis. Okay, so here's the proof. Fix a number. Fix a number, a whole number. Okay. And let cursive k sub m be the intersection of the as little m moves from one capital M, k m over m, one over m. Okay, so this is the y naught, and this is our epsilon. Right. So the picture is right that you have your cube, right, and you're taking your y naughts at 1 over m, 2 over m, 3 over m, 1 over m, 2 over m, 3 over m, etc. up to 1, right, m over m. Right. And you're taking your epsilons all to be 1 over m. Okay. So the epsilon, right, what you know is that between here and here, if you take any intersection, any intersection with, I'm sorry, if you're in there, then there exists an eta such that if you take the intersection with that guy, then the set, the one-dimensional Lebesgue measure, that set is smaller than 10 epsilon, that's say 10 over m. Okay. So in that case, right, then for any k in this intersection of these special sets, any horizontal slice of k at height y, you slice at any y between 0 and 1, it has Lebesgue measure smaller than 10 over m. Right? Because the fattened guy will have size smaller than 10 over m. So certainly, if you slice k itself, it will have size less than 10 over m. Have measure less than 10 over m. Okay, so suppose k is in the intersection of all these guys. Right? That tells you that all horizontal slices have measure 0. Right? Because it's smaller than 10 over m for every m, right? And so it has measure 0, right? And so k itself, the measure of k is 0. Right? If all the slices have measure 0, right? And you integrate over all the slices, and you get the two-dimensional Lebesgue measure, and you get 0. However, this thing here, the intersection of km is an intersection of open dense sets and is thus generic. It's an intersection of generic sets. Right? It's an intersection of generic sets. Its complement is going to be the union of, is going to be a countable union of sets of first category. Right? If you take the complement of this guy, right, it's going to be the union of sets of first category. The union of sets of first category is still a set of first category. Still a set of first category. And so let's just say that its complement is a first category, so it itself is generic. Right? By De Morgan's laws. Right? Is that okay? Right. This guy is going to be generic. To show this guy's generic, you need to show that its complement is a first category. Well, its complement, what is its complement? The complement of an intersection is going to be the union of the complements, like De Morgan's laws. Right? So the union of the complements, each of these guys is open dense, so it's a union of complements of open dense sets. Right? Complements of open dense sets are closed and nowhere dense, in other words, a first category. Right? And so you've got a union of sets of first category, a countable union of sets of first category, and so the complement is also a first category. So like, the complement of this thing is a first category, and so itself is generic. Okay. So this thing is an intersection of open dense sets and is generic. Right? Being generic, so what we see is that this guy consists of sets of measure 0 and is generic. Right? So the set of interest, right? The set of guys of measure 0 contains this thing. Right? Contains this thing, and so is itself generic. Thus is itself generic. Because the complement will be even smaller. It will be even more nowhere dense. Okay. So that is the sort of outline. That's the big outline of it, right? But we've skipped the main difficulty, which is proving the technical lemma that this thing is open. That this thing is actually open and dense. In cursive K using the Hausdorff distance. Okay. So now let's get to that. Those of you who came in late, I said that I'm not sure how much material we have today. So this could finish early. If it finishes early, then I'm going to give a presentation on something that has to do with Muckenhaupt weights, something that's very dear to my heart, Muckenhaupt weights. So it'll be a talk that I gave some years ago. But I sort of stopped working on it at that time, right when I thought of a good question. Maybe inspire somebody to think about that. Okay, so here we go. The technical lemma. So here's our lemma. We want to show that the claim is that for each y naught and 0, 1, and epsilon greater than 0, this set k y dot e is open as this with respect to the Hausdorff distance. So first part is it's not so bad. We'll show that it's open. Okay. So let K be some set in here. Then of course, for that, since that set is in here, we know there exists a fattening such that blah, 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 right? There exists a fattening such that, like, for all y in y naught minus epsilon, y naught plus epsilon, the intersection of that line with the fattened thing has measure less than 10 epsilon. The one-dimensional measure of the set of x's such that xy is in the fattened value smaller than 10 epsilon. Okay. So this one's pretty straightforward. For any k prime in K, such that the distance of k prime is smaller than eta over 2, we have that k prime is of course contained in the eta over 2 expansion of k, right, by definition of distance. And thus, k prime's eta over 2 expansion is contained in k eta. K prime's eta over 2 expansion is going to be contained in k eta. Right? But that tells you that the eta over 2 expansion of k prime is contained in this set where the intersections with the lines satisfies our condition, right? So if this set satisfies the intersection condition, this set's going to satisfy the intersection condition, right? Because it's contained in it, right? So the set of, right, the set of x such that xy is in k prime eta over 2 is smaller than the set is contained in, and thus smaller than, it has smaller measure than x1 in k eta, right, which is smaller than 10 epsilon. Right? So that's pretty straightforward, right? K prime has an expansion that satisfies the intersection condition, right? Because k eta satisfies the intersection condition, and k prime eta over 2 is contained in k eta. So k prime to the eta over 2 satisfies the intersection condition, and so there is an expansion of k prime that satisfies the intersection condition. So k prime, right? So k prime is also contained in k y naught epsilon. This is saying that every everybody in this 8/2 ball, everybody in the if K is in the set, then this 8/2 neighborhood of K is contained in the set. Right? In other words, it's an open set. K is an interior point. Thus, the ball of radius 8/2 around K is also contained in here. So K1 epsilon is something. Okay, second part, density. We want to show that given any point in cursive K, any point in cursive K, and any delta greater than 0, there exists some point in cursive K, y naught epsilon, such that the distance from K to K time to that point is smaller than delta. Right? That's density. Let me go backwards and erase here. So I'm going to need this. Okay. So, okay. So, let me introduce a little bit of notation. Let L(x theta) denote the line looks like this. So here's our cube again. Negative a half. This is L0. Line L0. Line L1. And we're going to, so there's a height, we fix the height y naught epsilon. There's a height y naught epsilon. Okay. And we're going to let L(x theta) denote the guy that intersects this guy intersects the line y equals y naught at position x, and having angle theta with the vertical axis. So this guy is this thing is we're going to call this is let L(x theta) be this. I think so we're going to have like from negative pi over 4 to positive pi over 4. That's how we're orienting things. Let theta n be defined as negative pi over 4 plus n times 1 over 2n. Pi over 2, n times pi over 2. Maybe explain it. Maybe it makes more sense to write it this way. N over n times pi over 2. Okay. as n ranges from 0 to n minus 1. Okay, so all you're doing is you're taking negative pi over 4 to pi over 4, this range of angles, and then you're dividing it into n. You're dividing this thing into n parts, and you're calling each of those endpoints theta 0, theta 1, theta 2, up to theta n minus 1. And let I sub n denote theta over n, theta over n plus 1. Okay. So I sub n denotes the nth interval. So you partition negative pi over 4 into n subintervals, and let I sub n denote the nth subinterval, and theta sub n is the left endpoint of that nth interval. Okay. Okay. So we're trying to show density, given any guy in the big space, and given any ball around any guy in the big space, there must be somebody in that ball. There must be somebody in here in the K line epsilon that's in that ball. So so fix K in the radius space. And delta bigger than 0. And we're going to create, we'll create K prime in K epsilon as K prime will be the union of two sets, A and B prime, as follows. So the first part is going to go like this. Okay. So first we're going to create A. This will be A. First note that for each theta n, there exists a point xn in -1/2 n such that L xn theta n is in K. Right? K is in cursive. This is pretty. Maybe it's hard to remember what's going on. Remember what cursive K is, right? Cursive K is the union of, it's the collection of sets for which, for every angle between -pi over 4 and pi over 4, there is a line segment at that angle, right? So you know that, in particular, for these angles, right, for these chosen angles between -pi over 4 and pi over 4, you know that there's going to be some line segment in there at that angle. Okay, that line segment is going to intersect the line y equals y naught at some point, right, with x coordinate x of n. That's what we call x of n. Okay, so this picture, right? You have your K. K has all angles, right? K has all angles in it. Segments of all angles. In particular, it has somebody for each theta n. There's going to be somebody in there of angle theta n. So let's say that this guy is the angle of theta n. Well then, look at height y naught, right? we know that right, that will intersect at some point. Call that point x of n. This line is L x of n, theta sub n. Okay. So for each theta sub n, there's a point such that this thing lies in the K. And so what we do is we then for each n, let S of n, capital S of n, be the union of lines through that point. Okay? Fix that point and take the union of lines through that point where theta lies in, the theta ranges over in. Remember what in was? It was theta n plus 1. Right? So S of n, we fix that guy, L x of n theta sub n, right? And what we're going to do is we're going to throw in all lines that pass through this x of n y naught, and the angles at angles ranging from theta n to theta n plus 1. Okay. Theta n plus 1. So we're going to throw in all lines that whose angles who pass through this point and whose angles go through a certain range. Okay. So the angle of this, the angle here is pi over 2n. Right? The angle that we span here is pi over 2n. Right? Because of how we define it. We do pi over 2 divided into n parts. And this is one of those intervals. Okay. Okay. And so we let S of n is going to be that double triangle thing, this union of line segments. And then we let A be the union of the S of n's. So for each of those points, we take we take the union of those double triangles and we reunion them all together, and that's going to be our A. Okay, so now you notice this. You say, well, look, if we take if we choose n large enough, right? If we choose n large enough, then each of these things is not going to differ from the original line. So here's the original line. Right? Here's the original line. That original line is in K. Right? That original line is in K. And if we choose our n large enough, then no point in the set is going to be more than delta away from the original line. Right? We've chosen our delta. You think like this. You cover this thing with a delta neighborhood, right? And then you choose your n large enough so that when you moved over, you're still within that delta neighborhood, right? Because your n is up to you, and you just choose your n huge, right? You have your thing here. You have this delta 2 around it, right? You choose your n big enough so that the angle is such that that you don't leave the delta 2. Okay? If you choose your n large enough, then every point in A will be in the delta tube. I'm sorry, in the delta neighborhood of K. Really, every point in S of n will be contained in the delta neighborhood of S and theta. That's really what we're saying here. And at this point, Stein makes the comment that further, if your S of n are not contained in Q, you just shift them over a little bit so they are contained in Q. This point I'm not really clear about, so let me I'll mention it, but I'm not, I understand what he's saying, that, well, when you, it could be that when you have an angle over here, when you sweep it out a little bit farther, you leave your cube, right? In that case, he's saying just slide it over back into the cube. Okay. But I'm not exactly sure. That point, I'm afraid I haven't thought about much. So there's something that I haven't fully checked. But in any case, what ends up is that you get that A is contained in the delta neighborhood. A is contained in the delta neighborhood of K. Okay. So if we had the opposite inclusion, then we'd basically be done, right? If we had the opposite inclusion, we would be done, right? Because then our A would be our K prime. Right? We would have created a guy. Well, we still need to check some things about it, but we'd be almost done. So anyway, at this point, we still need to fix it up a bit. And now I see there's no way we're going to get to my old lecture. Just do that. Okay. We want to, but we do want K prime we want K prime so that K is contained in K prime delta. Right? Right now we have, our K prime, we just have part of our K prime, and we see that its expansion, it is contained in the delta expansion of K, but we'd also want the opposite statement. We want K to be included in the K prime expansion, in the delta expansion of K prime, but we don't have that, so we need to fix up our K a little bit. Okay, so the second part is mainly, this A prime is mainly to address this point. And it's pretty simple, say, okay, so we fix up K prime by including the following. Okay, so we just fix it up a little bit. So here's what we do. Recall, K is a union of lines. Okay? Being in the set, it's a union of lines. But then, if we take the delta expansion of each of these lines, we take the delta neighborhood of each of these lines, this is an open cover. Okay. K is compact. So there's this finite subcover. Basis of finite subcover, delta M, n from 1 to capital M. Okay. Well, then let A prime, create a union of those lines. Just throw in those lines, right? Right? If we throw in those lines, then when we take the delta expansion of it, it'll cover K, right? As we just said, K is covered by the delta expansion of these lines. So we've got a finite bunch of lines, and we just throw those lines into K prime. So let then K prime be A union A prime, and then K prime's expansion will cover K, right? Because it includes this thing which covered K. Notice that A prime is already included in K, right? A prime is a subset of K. So, since A prime is a subset of K, we don't have to worry, K prime is certainly included, right? K prime being A union K prime is certainly included in the delta expansion of K, right? Because we already saw that A is included in the delta expansion of K, and A prime itself is already included in K without any expansion, right? So K prime is included in K prime is included in K, in the delta neighborhood of K, and so we've created, so thus, right, the distance between K and K prime is smaller than delta. You guys getting it? You see, this is really like being a mechanic or something, right? It's like, I want to create something that's close by. Okay, here we go. We're gonna build it. Oh, it doesn't work. Okay, let's tinker with it a little bit. Okay. Okay, but so we still need to check the fact that this K prime actually does lie in this set. Right, it has to satisfy the intersection condition. Right, it has to satisfy the intersection condition. So, here we're doing A prime. So part 3, we still need to check that K prime is contained in this thing. In other words, that it satisfies the intersection condition. So fix any point y in y naught minus epsilon, y naught plus epsilon. And consider the intersection consider this intersection. Consider the intersection at height y of the line with the A set. Okay, and then in a second we'll expand. We'll fatten it. Okay. So remember what A is. A consists of y naught. Consists of things that look like this, right? You have some line x and theta n, and you have this thing of angle pi over 2. you have these guys, and then there are n of those guys. Right? So recall A is the union of the S of n's, where the S of n's, each of these things is an S of n. Each of these things is an S of n. And so now what we're doing is taking a y that's nearby, y plus epsilon, y minus epsilon. We're taking a y nearby, and we're looking at the intersection here. Right? So it will, it consists of integrals, right? Of n integrals, right? The intersections of the line with these double triangle lines. It's possible to see via trigonometry that the intervals from the flattened set A eta have lengths smaller than 8 epsilon over n plus 2 eta. So you fatten these guys, right? It turns out that each of these, because the angle is pi over 2n, it's possible to see that the length of these guys, because the angle is pi over 2n, and the farthest away can be is eta, right? The farthest y can be is from y naught is eta. You can see that these lengths is smaller than 8 epsilon over n plus 2 eta, right? And so the measure of the set of the intersection with A eta is controlled by n times that, by 8 eta plus 2 n eta. So we control the intersection of the A part, and then we control the intersection with the A prime's expansion. Right? So A prime is even easier. Right? A prime is easier. It consists, right? A prime consists of line segments, of m line segments. Right? It's not, right? It's just a bunch of lines, right? L1 through Ln, right? So when you intersect, you just get n points, right? And then the fattening is just going to be, the fattening of those points will result in integrals, right? So the intersection at height y, intersection with the line at height y consists of n points. Right? And so the measure of the set of x's such that xy is contained in A prime eta is bounded by m times 2 eta. Okay. Each of those points fattens out into an interval of width 2 eta, right? Because you're taking the eta neighborhood, right? And you've got m of those points, so it's controlled by that. Okay. And so you add it together, right? And so adding those two blocked off things together, you see that this thing is controlled by 8 epsilon plus 2m plus n eta. And so just choose eta smaller than epsilon over m plus n. And you get a 10 epsilon on the right side. remember eta is up to us, right? We get to choose our eta, right? So choose eta small enough that that thing is smaller than epsilon over n plus n. So we have actually found a point that is not only close by to k, but also is in the special subset cursive k, why not epsilon? In other words, this guy is not only open, but also dense in cursive k. D. I'm just going to freeze here. Yeah.
Can you repeat that last bit?
Yeah. So what are we trying to do? We're trying to show that the k prime that we created satisfies the intersection condition, right? That if you intersect at any height between y naught minus epsilon and y naught plus epsilon, then the size of that intersection, its Lebesgue measure, one-dimensional Lebesgue measure, is smaller than 10 epsilon, right? And what we do is we say, okay, well, let's look at it in pieces. Well, the k prime consists of a and a prime. Let's look at the part that comes from a. Right? Well, a is going to be is going to be a union of n intervals that you get. Right? What's a? A is a union of these double triangles. Okay. And there's n of them. And we know that the angle here is pi over 2n. That's how we construct it. Right? Okay, so then when you fatten it, you end up that the length of those guys is controlled by 8 epsilon over n plus 2 eta. And there's n of those guys. So altogether, the intersection with the fattened guy, is going to be smaller than n times that. So that's 8 epsilon plus 2 and eta. Now then you also have a prime. A prime was a bunch of lines, right? It's not the double triangles anymore, it's actually just lines, right? These lines, right? L1 through L capital N. Right? L consists of M line segments. Well then when you intersect, you just get points. Right? Well then when you intersect with the fattened version, those points, right? If you fatten these guys up and you intersect, you get intervals. Right? At worst you get m disjoint intervals, each of length 2 eta. You get m disjoint intervals, each of length 2 eta. So the intersection is controlled by m times 2 eta. Right? So that's from A prime. You put those two things together, right? And you say, okay, well then, if we're looking at the total intersection, well, this is going to be controlled by this plus that, right? And so you get 8 epsilon plus 2 m plus n eta, right? And that depends on our eta, right? We remember being in here means that there exists an eta for which the intersection is smaller than 10 epsilon. So we choose our eta to be smaller than epsilon over m plus n. That makes this term smaller than 2 epsilon. And so the total is smaller than 10 epsilon. That's where that 10 epsilon comes from the trigonometry. That's it. Okay, so I hope the course wasn't too bad. I hope it had at least some fun parts in it. So the final, I haven't thought too much about the final, so let me try to think today what exactly will be on it, and then I'll send out a note. yeah, likely it will cover the stuff from the last exam up till now. So starting from sort of at an odd place, I'm afraid. It will start from Calvin-Zygmunt distributions, and then go to today's material.